This lesson focuses on mathematical relations or mathematical relationships. And our goals for this lesson include being able to represent two variable, in other words like x and y, relations in multiple ways, including graphs, tables, equations, ordered pairs. We're also going to be able to define the differences between continuous and discrete relationships and classify real-world scenarios appropriately. And finally, we're going to be able to identify the differences between independent and dependent variables. So if that's a lot of new terminology for you, don't worry, we're going to get into it right away. To get started, we're going to review the Cartesian plane. And it's called the Cartesian plane, if you're curious, because René Descartes, a French mathematician in 1637, decided that we should be able to describe different points using two intersecting axes. And the horizontal axis is always called the x-axis, usually, and the vertical axis is usually called the y-axis. And a couple other things, the point where those two axes cross is often called the origin, okay? And that is the point 0, 0, because you're not going left or right at all, you're not going up or down at all. These 4 points, A, B, C, and D, I've labeled. And at this point, if you'd like, you can pause the video and try to identify what those ordered pairs would be on the grid. So, with anytime we count right or up, we're counting in a positive direction. Anytime we're counting left or down, we're counting in a negative direction. And we always do our x, or our horizontal movement, before our y. All right, so for this A point, we're counting 1, 2, 3, 4 points right. So my ordered pair would be 4, and we're counting 1, 2, 3 units up. So that is the ordered pair for 3. B, well, I'm counting 2 points to the right. So that's positive 2, and I'm counting 1 unit down, so that is negative 1. C, I'm counting 1, 2, 3, 4 units back, so that's negative 4, and up 1 unit, so that's positive 1. And finally, D, I'm counting 2 units back, so that's negative 2, and 3 units down, so that's negative 3. In future courses, you're going to learn that each one of these quadrants has a specific number associated with it. Because this is all positive, this is quadrant 1, and then we just count counterclockwise. So this is quadrant 2, quadrant 3, and quadrant 4. And once you start doing more advanced trigonometry, this type of 1, 2, 3, 4 quadrants is going to come back into play. Now that we've looked at how to plot points on a Cartesian plane, we're going to apply that knowledge along with some other knowledge to solve a problem. So the problem reads 3 toothpicks form a triangle right here. Okay, a second triangle is formed by adding 2 more toothpicks. A third triangle is formed by adding 2 more toothpicks, and so on and so forth. So one of the core ideas in this unit is representing a relationship between two variables in multiple ways. So in this case, we're going to start off by representing that relationship as a table of values and as a graph. All right, so if you want to pause the video and try to do this on your own, you're welcome to do so. But in this case, triangle number 1 and the number of toothpicks is 3. Well, I just verbally told you what the relationship. With the second triangle, we added 2 more toothpicks, so that's 5. Third triangle, we added 2 more toothpicks. Fourth, we're going to just keep adding 2 more triangles. Okay? Now, when you have a table of values, the left column is always your x variable. Okay? And your right column is always your y variable. So I'll just put that up here, x and y. And we just looked at, on a graph, our x-axis is always our horizontal, and our y-axis is always our vertical. Okay? Now, I've got 2 choices because I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 points there. If I wanted to carry all of these through, I'd obviously need to extend my graph up a bit. Not going to worry too much about it. Instead, what I'm going to do is I'm just going to go up by 2's. 2, 4, 6, 8, 10, 12, and so on and so forth. Again, where they cross is the origin always 0, 0. And if I'm counting up, I'm always counting positively. On my x-axis, well, I'm just going up by 1's. So even though I chose to go up by 2's on my y-axis, I can go up by a different amount on my x-axis as long as I'm consistent. So 1, 2, 3, 4, 5, and so on and so forth. Now, to plot this out, 1 is my x, 3 is my y, so I'm going to do my best, because I don't have a grid here on this board, to represent this accurately. And I do know that it's going up by a steady amount, so I do know that my points should form essentially a straight line, so I've done my best on that. Now we're going to look at how do we write an equation, and how do we use that equation to solve more challenging problems. The third way we can represent a relationship is using words. And in this case, we're trying to write the relationship between the number of toothpicks and the number of triangles. And I think this is so simple that I'm going to clap twice and it's going to appear. And voila. Lots of ways to do this, but I've just described it as the number of toothpicks is 1 more than twice the number of triangles. So I see that if I doubled 2 becomes 4, 1 more. Doubled 3 is 6, 1 more is 7. And I worded this because when it comes to writing an equation, sometimes writing it in words can be very helpful. So now we've got 4 ways to represent the same relationship. We've got a table of values, we've got a graph, and we could actually even call this a set of ordered pairs, right? Because each one of these turned into an ordered pair that we represented on the graph. We've got words, and now an equation. So if I were representing this relationship as an equation, and let's say that I called the number of toothpicks big T, and I called the number of triangles, just to keep it different, let's call it M. I'm not sure why I called it M. All right, well, the number of toothpicks T is, well, it is in math means equals 1 more, so I've got plus 1, then twice the number of triangles. Well, twice the number of triangles would be 2 times M. And again, the order wouldn't matter. I could have put 1 plus 2M or 2M plus 1. So, some of you may have found writing the equation difficult, but I'd really encourage you to dig in and try to keep figuring out, as we do examples, how to write equations. Because writing an equation helps you to generalize a relationship. What do I mean by that? When we have an equation like this, now we can find the number of toothpicks for any number of triangles, or we can find the number of triangles for any number of toothpicks. And that's helpful. So for these 2 problems, I said the first one, use the equation to determine the number of toothpicks if there are 63 triangles. Well, I called my number of triangles M. So what that means is if my equation is T equals 2M, well, M in this question says 63. So I'm going to replace my M with 63 because this is 2 times M plus 1. Well, 2 times 63, I have to follow order of operations. That becomes 126. Add 1 is 127. So when there's 63 triangles, there's 127 toothpicks. Determine the number of triangles if there are 89 toothpicks. Well, I called toothpicks T. So now I can use my equation by replacing T with 89. 2M plus 1. Well, whenever I'm solving for a variable, I got to work backwards. I got to do the opposite. So to cancel out that 1, since it's being added, I'm going to subtract 1 and get 88. And because this is 2 times M, the opposite of multiplying by 2 is dividing by 2. And whatever I do to one side of an equation, I must do to the other. So m equals 44. In other words, there are 44 triangles when there are 89 toothpicks. Now, one last question that I forgot to tackle when I had the graph up is, should I have drawn a line through my graph? Because we talked about discrete, or I brought up the terminology of discrete versus continuous. So we are going to have that conversation and define those two terms right now. So we have to get two terms clarified in our minds. First one is discrete variables. And a discrete variable is a graph of unconnected points because only certain values make sense for that context. For example, the problem we just did with the toothpicks. Well, it wouldn't make sense for me to say, oh, 1.5 toothpicks or 4.2 triangles. There are only certain values where that would make sense. So that's why I never drew a line through that graph. Sometimes, though, we have what's called continuous variables. And that's just a graph where you connect points over a given interval. Sometimes from infinity to negative infinity, but sometimes only within a range of values because every value in that interval makes sense for the context. And we're going to look at a continuous graph in our next example. As always, you can pause the video when you read an example and try it out on your own if you'd like. For our second example, it says physics students determined the resistance in an electrical circuit by measuring the voltage V when a current of I amps passed through it. Now, in this case, we've been given a table to represent the relationship between those two variables. Sometimes you'll be given a graph, sometimes, like in our previous question, you'll be given a drawing. Sometimes you'll be given an equation. So you'll always be given a starting point, and then most of the time you're going to be asked to represent that relationship in other ways. Well, in this case, we're going to start off by taking that table and transferring it onto a Cartesian plane, onto a graph. So very similar to the previous example, but in this example, our table is horizontal. So a couple tips for you. When you're given a horizontal table like this, a little clue is that our top variable is always our x variable, and our bottom variable is our y variable. And those two variables have significance in many problems, not all problems, but the y variable is what's called our dependent variable. In this case, voltage depends on how much current is passed through it. So the y depends on the x, okay? And so we'll make sure we define that at the end. But in this case, you can either put, in this case, I might put V and I. And just like our previous example, when I'm looking at these and I see that these are all multiples of 6, on my y-axis, I'm going to go up by 6s. Okay? 6, 12, 18, 24. And notice how I am not labeling every single point. And that's okay, as long as I know that the crossing point is my origin, 0, 0, and I go up by a steady amount there. In some future lesson, we'll look at how to do what's called a compression on a graph, but we haven't had to do it on this, so we're not going to worry about it for this lesson. Here, I notice that all of these are a multiple of a half, so I'm going to go every 2 ticks on my axis, I am going to count 1, so that means that every tick represents a half. Now for this, a half was 6, 1.5 was 18, and I am going to once again notice that this is a linear relation, meaning that it goes up at a steady rate, not that it's connected by a line necessarily, but we'll talk about that little feature in a second. All right, but a linear relation just means it goes up or down by a steady amount. All right, now, there's our graph. The next question is, should you connect these with a point? In other words, is this a discrete relation or discrete variables, or are these continuous variables? Well, the question you'd want to ask yourself is, could I put any amount of current through a circuit, and would that produce a corresponding amount of voltage? And the answer is yes. I could put in literally 0 currents into a circuit, and that would produce 0 amps. And I could go on and upward. I could give more than 4 amps. Now, I don't know what the upper limit is, but for this example, I know that I can do 0, and I'm going to hope that I drew these circles in relatively straight line, and I'm going to go up there. Okay? So, the reason why I'm connecting these is because, for example, and it says on letter C, use the graph to determine the voltage for 2 amps. Now, many of you would look at this table and you'd say, well, that's easy. I'm going up every half, I'm going up by 6. Absolutely great. Using the table is good. For this one, we're going to just use the graph, my imperfect graph, and we're going to do something called interpolation, which just means I'm reading points within a given range of data. So in this case, if I go up vertically from 2, that is my value, and now I'm going to shoot across, and I'm going to hopefully, now I obviously didn't draw this perfectly because I'm getting somewhere around 21. I know that it should be 24, but that is how you interpolate using a graph. You take the value you're given, go up or go over, and then try and find the corresponding ordered pair. We're going to again try to tackle writing an equation, because that's a skill that we're going to build over this unit, and then we're going to use that equation to solve a quick problem. So it says write an equation expressing V in terms of I. And that's pretty common when we're writing linear relations, in other words, ones that are going up or down by a steady rate. We usually start off with our dependent variable y, okay? And so when I say V in terms of I, that means we're going to go V equals something. Well, with this one, you can do a bunch of things. I just noticed that 36 is 12 times bigger than 3, and I noticed that 48 is 12 times bigger than 4. So here it is simply 12 times I. And if I recall back to my graph, I noticed that it hit 0, 0 also. So I could, if I filled in 0 for I, it would produce 0 for B. I could take any value here, plug it in for I, and it would give me the corresponding voltage. Okay? It would need to work for at least 2 points. So with our last question here, use the equation to determine the voltage of 7.8 amps. Well, that is simply voltage equals 12 times 7.8, which is 93 6/10 amps. All right, so now we've looked at a discrete graph, we've looked at a continuous graph, and we're almost done. Before we wrap up, we're going to define 2 terms that are going to come up a lot in this unit: independent variables and dependent variables. And independent variables, as have been mentioned in this lesson, are just the inputs of a relationship. Independent inputs. They are always represented on the horizontal or the x-axis of a relation, and therefore they're always the first coordinate of an ordered pair, because an ordered pair is always xy. The dependent variables are, conversely, the outputs of a relation. And so they are always represented on the vertical or the y-axis of a relation, and they are always the second coordinate of an ordered pair. For example, if we took the formula A equals pi times radius squared, the formula to find the area of a circle. Well, radius would be our independent variable, because the area of a circle depends on the radius. And in this formula, we would always take values, input them for r, and that would spit out a value for a, and that would be how we could create a table, create a graph, however we wanted to represent this relationship that is currently in the form of an equation. If we want to represent the relationship between the altitude of a plane and the time it's in the air, well, the altitude of the plane depends on how long the plane is in the air. Therefore, our altitude would be on our vertical axis, and time would be in our horizontal axis. I hope this lesson has helped you to understand a bit about discrete versus continuous variables, about independent versus dependent variables, and about a variety of ways in which we can represent a relationship between two variables, x and y, or whatever letters we want to. Things like tables, graphs, ordered pairs, equations, words, because we're going to use these concepts throughout this unit.